Hi class, welcome back. This tutorial will also use the supported vector machine and neural network models to make the classification decision. Well, we will use the income dataset, which we used in our decision tree tutorial. So let's first import this income dataset. And we name it as income original. And let's check the summary and the structure of this dataset. Well, you can see this is a pretty large dataset because it consists of 32,561 observations. And because the time needed for building a neural network model is pretty long, so we will use the sample function to select only 2,000 rows to speed up the execution time. So here we still load the current library and we set seed equals to 500. Well, here you can see that we use a sample function to randomly select 2,000 row index and include those 2,000 rows into the new data frame called income. So the first parameter for the sample function is the range for the rows. So we have from 1 to the total number of this dataset. And we want the second parameter is the number of rows you want to select for your new dataset, for your sample. So here we only want 2,000 different rows, so we set it as 2,000. So we now have a new data frame called income, and it only has 2,000 different rows, 2,000 observations. And let's check the distribution of our target variable. So you can see because we randomly select this 2,000 rows, this sample, so the distribution for our target variable is the same. And next, we will split our new data frame, the income, in an old fashion which we repeatedly used before, which means like 50% of our instance will belongs to training data set and 25% will belongs to testing data 1, testing data 2. So let's run this chunk. And then now we have the training and the 2 testing data sets. We will build a supported vector machine model using SVM function, and this SVM function is from the library curlab. So we first load this library. And notice that the function is exactly the same function we used for the supported vector machine regression model. We just replaced the numeric target variable with this categorical, this factor variable, target variable. And we still use the default C value and the kernel RBF dot. So this model is also built on the training dataset. And then next we use predict to generate the class prediction for the class level for income of the test data 1. And because our target variable now is categorical, is a factor variable, we can now use confusion matrix to generate a confusion matrix and also the precision recall and so on, and also the M matrix to generate the accuracy, precision, recall, and F measures, and so on. So let's use this predict function and the confusion matrix I matrix function to generate a prediction and also see the evaluation results. So let's run these few our commands. Similarly, for the testing data 2, we use the same function predict, confusion matrix, and M matrix to generate prediction results and evaluate those results. And next, we will use the multi-layer perceptron model from RYCAT to build a neural network model for making classification decisions. So we will still load the RWCA first and use the make-WCA classifier to locate and simplify the name of this model. And we now use the trained data to build the neural network model using MLP function. And you can see here, similarly, income is a factor variable. We can use both numeric target variable and factor target variable for both regression model building and classification model building. And well, we see here we have WCA control n equals to 50. This n is the number of epochs. So let's build this model. Well, it may take a few seconds because we know that this multi-layer, when you have a large data sets, and if you set this n give a large value to the n parameter, it will also take a longer time to execute. And similarly, we use predict and metric functions to generate the prediction for the testing dataset and evaluate the predictions. So let's compare the evaluation results from both supported vector machine model and the neural network model. In terms of the overall accuracy, supported vector machine can reach about 55% of accuracy. However, the neural network only achieve about 77% of accuracy. Well, for the precision one, so for the negative class, the class with target variable equals to less or equal to 50K. In terms of precision, well, the neural network performs better than the supported vector machine. In terms of the recall, supported vector machine performs better than neural network, while the overall F measure for the less or equal to 50K class, the supported vector machine performs better than the neural network. Well, however, for the positive class, which is larger than 50K class, in terms of precision, supported vector machine outperform the neural network, but in terms of recall, neural network outperforms supported vector machine. Well, their F measure values are really close. We have discussed two different approaches using both loop or the list apply function to conduct the n-fold cross-validation for the classification evaluation. Well, here we still use the three-fold cross-validation for both supported vector machine and the neural network models. So similarly, the steps are the same, basically the same. Instead of using the 6 error measures and R-square and correlation coefficient, now we change them to accuracy, precision, recall, and F measure. We append the evaluation results from each iteration to this KSVM total result array, and we use row means to generate the average value for those evaluation values. And we tried both ways. The first way is using the loop, and the second approach is using the list apply function. So let's run this chunk. So this is our average evaluation values by using threefold cross-validation. And next, we will also apply this threefold cross-validation for the neural network model. And we still use n equals to 50. So instead of using loop, because this MLP model is from RWCA, we can simply using this evaluate WCA classifier with number folds equals to 3. This will automatically compute the three-fold cross-validation for us. So we can use both of the approaches. Oops. Yeah. So let's run this chunk. Well, when you build this multi-layer perceptron model, you have to be patient because if you have a large data set, it always takes a longer time to execute. So after a while, this is the average evaluation results we got from this threefold cross-validation for our neural network model. And next, we still gonna change some parameters for both neural network model and the support vector machine model. So for neural network model, we can change the L, which is learning rate, the M, the momentum rate, and the H, the hidden layer numbers, and also the N, which is the number of the epochs. And next, for the support vector machine, you can change the kernel value and also the value for the C parameters. And so these steps are also similar to the steps we described in our last tutorial when we built a support vector machine and neural network regression models. So we can just run this chunk. It may also take a longer time because it is like threefold cross-validation for each parameter changing, so it will take some time. So this is the end of this tutorial. We didn't change much our commands from the last tutorial, which we used the support vector machine and the multi-layer perceptron models to build the regression models. So the only thing we change is change the target variable from a numeric variable to a factor variable. And also we change the evaluation measures. So we altered the 6 error measures, the correlation coefficients, and the R-square to the overall accuracy, recall, precision, F measure, confusion matrix, and so on. So thank you for your time and thank you for listening. Bye.